Alrighty, so this is the last part in the periodic trends. By now, you should hopefully know what shielding, nuclear effective charge, and what the distance from the nucleus are, and how those affect attractive forces. If you do not understand those or don't know those already, you should definitely watch the video that actually talks about them for shielding and nuclear effective charge. That video should be titled Attractive Forces. Now we're going to talk about a series of periodic trends that we can essentially just use the periodic table to compare and contrast different elements. So the first one that we're going to look at is atomic radius. Atomic radius is known as 1/2 the distance between the nuclei of two atoms of the same element when the two atoms are joined together, or if you want it in super simple terms, the size of an element. So it's basically just how far the nucleus of an element extends to the valence shell of that same exact element. The way that it's measured is by taking the atomic radius, or basically you take two of the same exact atom, stick them right next to each other, and measure the distance from both of their nuclei. What you essentially end up getting a measurement of is how large or how wide that element itself is. Now, the nice thing is you can measure this or get a qualitative assessment of the atomic radius just by simply looking at positions on the periodic table. Now, there's two trends that go along with it. We have that atomic radius decreases going from left to right, and you have that it increases going down a group. Now, the reason why atomic radius decreases going from left to right simply has to do with the fact that shielding does not change as you go from left to right. Meanwhile, nuclear effective charge is increasing. So the reason for this is because shielding is constant and because nuclear effective charge increases in the same exact time. Now, the reason why atomic radius increases going down a group is because as you go down a group, shells are added, and shielding also begins to increase. Remember that because nuclear effective charge is increasing as you go across a period, that means that electrons become more attracted to the nucleus. So those valence electrons or those shells will begin to compress themselves. Meanwhile, as you go down a group, obviously, if you add more shells to an element, then you're going to expand the radius of it. And also, as you increase the shielding, the attractive forces end up being lowered. If you have a periodic table next to you, it helps to pretty much set up these lines that show you the trend itself. So if you wanted to, you could take a sample periodic table and show that as you go from left to right, atomic radius decreases. And as you go from the top to the bottom, you could say that atomic radius increases. Okay? That's the first out of the four trends. This is one of the main ones that we spend a lot of time talking about, shielding and all that sort of stuff. Now let's go ahead and quickly just show a diagram that shows everything that I said. Going from left to right, atomic radius decreases, so elements to the right are smaller than elements to the left. And going from top to bottom, atomic radius will increase. Our next trend that we're going to look at is electron affinity. Electron affinity is just a measurement of how likely an atom is to how likely an atom is to gaining an electron. And the trend goes via this path. So it increases going from left to right, so across a period, and it also increases going up a group, so bottom to top. The reason for this trend is because as you go from left to right and from bottom to top, electrons will become more attracted to that center nucleus, and thus they are more likely to be added on to a certain atom. So when you're taking your periodic table, you're going to draw two lines. It's obviously going to be one going from left to right, showing increase, and one going from the bottom to the top, also showing increase. So here, Electron affinity increases going left to right, and electron affinity also increases going top to bottom. Both of these arrows are pointing in the same exact direction, so they're going to the top right, so you can combine the two to make one big diagonal arrow. What this is saying is that elements to the top right have a higher electron affinity, while elements to the bottom left have a lower electron affinity. Next up, really quickly, here's the periodic table itself with this trend. Next up, very similar to electron affinity, we have electronegativity. Electronegativity is just the measurement of how much an atom attracts a bonding electron. A bonding electron is exactly what it sounds like. It's an electron that's used to make a bond with another atom. And luckily, just like electron affinity, electronegativity has the following trend where it increases going across a period or left to right, and increases going up a group or bottom to top. Remember that the main difference between electronegativity and electron affinity is simply that electron affinity involves just regular electrons being added, while electronegativity requires bonding electrons. Besides that, they are very similar measurements and they go via the same exact trend. You would essentially draw the same exact arrows that you just drew for electron affinity that you would for electronegativity. And here you'll see the trend. This is just one of few scales used for electronegativity. Regardless of which scale for electronegativity is being used, you'll always see that fluorine is the most electronegative atom, meaning that it holds on to bonding electrons significantly more than any other element. And the very last periodic trend is ionization energy. Ionization energy is the opposite of electron affinity. It's the energy required to remove an electron from an atom. This should be pretty obvious, but if you have an electron that's more attracted to a nucleus, it will be harder to remove, thus having a higher ionization energy. If you have an electron that's not that attracted to the nucleus, it's going to be easier to remove, so it'll have a lower ionization energy. Now, despite the fact that it is the opposite in terms of definition to electron affinity, it goes via the same exact trend. It increases going from left to right, and it increases going up a group. Here, it just says that it's decreasing going down a group, but means the same thing. Decreasing going down a group just means increasing going up a group. For ionization energy, you should be expected to use shielding and nuclear effective charge to explain it. So if you're comparing two elements and one of them has higher shielding, so let's say we're comparing element X versus element Y. And let's say, for example, element X has more shielding compared to element Y. Remember that increases in shielding lower attractive forces. So because of that, element X will have a lower ionization energy, or IE for short. We can also use this same exact logic for nuclear effective charge. So if we're looking at the same exact elements, let's say X and Y, and let's say hypothetically element X had a higher nuclear effective charge. You should hopefully recall that increases in nuclear effective charge end up increasing attractions to the nucleus. If the electrons are more attracted to the nucleus, then they'll obviously be harder to remove, so then it'll have a higher ionization energy. Okay. And again, recall that the trend goes as follows. Ionization energy increases going left to right, and it increases going bottom to top. And those are the only periodic trends that we need to concern ourselves with. And of those four, you only need to explain ionization energy and atomic radius in terms of shielding, nuclear effective charge, and distance from the radius.